Hello, this is Jason Chanko, Applications Marketing Manager at Siglent Technologies America. And in today's video, we're going to cover the basics of spectrum analyzers, just so some of the uses for people that aren't familiar with what a spectrum analyzer is and what it does. So, what is a spectrum analyzer? Pretty simple question to answer. A spectrum analyzer is a test instrument that displays the amplitude versus frequency for an input signal. So here we've got a picture of the Siglent SSA 3000X series of spectrum analyzer. As you'll notice, it's got an RF input here as denoted by that arrow, and it's just going to display the amplitude versus frequency for an input signal. Now, some common uses for a spectrum analyzer include monitoring broadcasts and transmissions. This would be FM, AM, Wi-Fi, Bluetooth. So anything that we're communicating wirelessly from one place to another, we may want to see what the amplitude is and over what frequency ranges we may be concerned with. Another application area would be RF component and subsystem testing. This could include antennas, cables, amplifiers, filters, any number of RF components or subsystems. We want to make sure that they're operating over the correct frequency range and delivering the amplitude that we expect without any interference or any kind of other problems that we may see in that particular output. And then we've got electromagnetic interference and pre-compliance testing. This is a little bit more specialized. This would be for companies or people that happen to be ready to sell their product. The governments will regulate the amount of interference or the amount of RF output over particular frequency ranges that product can or is allowed to emit. And so we want to make sure that we're underneath that particular limit line or under that particular limit set before we go through actually selling the product, because if it goes out into the field and it's not meeting those requirements, it can be recalled and lead to fines and a bunch of other nasty things. So we want to avoid that at all cost. And so now we'll dig into a little bit more on each of those applications. So monitoring broadcasts and transmissions, what are some important things that we need to take a look at? Is the transmitter doing what we expect? Are we reaching the amplitudes that we expect? Are we in the transmission band, or are we covering the right frequency range, or are we going outside of our expected frequency range and stepping into someone else's frequency range? Far field pattern testing. Are we transmitting properly in a particular direction? Are we expecting a certain amount of output power at a particular point in time or space, and we're not actually getting that? So you can walk around your transmitter or drive around your transmitter even and test in different places to make sure that you're getting the right amount of power where you expect it. We can also do site surveys internal to an office building or a hospital. What channels are occupied? If we have lots of communications going back and forth, that can also lead to some interference. So we can take a survey of what transmitters are in a particular area, and we can start to get a better idea of where we may have some interference or some issues with occupied channels. For monitoring broadcasts and transmissions, I wanted to set up a little bit of a demo here in which we have an FM antenna, and we have this spectrum analyzer set to 92.3, which happens to be a radio station here in Cleveland, Ohio, and it's an FM radio station. And what we're going to do here, or what I'm showing, is the yellow trace is actually outlining the FM. So this is the FM voice section. And then we've got two sections to the left and to the right of that center frequency. Again, frequency modulation. We're going to have the voice information is going to be transmitted that way. Then we've got these two digital channels that are transmitting the information for the HD or digital radio. Many of you may be aware that, when you're in a more modern vehicle, you're listening to the radio, it will actually tell you what song is playing and the artist. So that information is actually held in these side bands over on this or on either side of that center frequency. So what we're doing right now is monitoring an FM transmission. Again, this is a useful tool for this particular job because we're visualizing the actual output. Now the purple trace that we have here is a secondary trace. You can access that by pressing trace. Here with this instrument we've got 4 traces available. You'll see clear right. Clear right is the trace type that we show with the yellow trace, which is trace A here, and that's actually overwriting. Every time we've scanned through that particular frequency span, we're getting new values for each individual frequency bin. And purple here is going to, which is B, is in max hold, and that max hold is then going to show us the maximum values. So over a span of 10 minutes, we actually get the envelope that this particular transmission is also taking up. Some other nice features with instruments like this: we've got a demodulation. We have FM and AM, so we can actually use the earphone plug here and the earphone monitor here. We can enable it and do an FM demodulation on the voice data. And in that way, we can actually listen to this particular transmission very much like we would listen to a regular radio station on our car, only we can actually visualize the width that we're actually occupying for this particular transmission. So again, spectrum analyzer is very helpful for being able to monitor transmissions, being able to tell whether you're stepping outside of your particular given band, or if someone else is stepping outside of their band and happens to be infiltrating the bands next to them. So it can be a very helpful instrument for that particular measurement type. The next application space I'd like to take a closer look at is going to be RF component and subsystem testing. Is the component or subsystem doing what we expect? If we expect it to be outputting an amplifier to output 10 dBm, is it actually going to do that with the given input? And is that going to work over a particular frequency range? Or is our filter working correctly? We can detect spurs, harmonic distortion, and intermodulation because the spectrum analyzer is going to allow us to visually see exactly what's happening with respect to frequency in that particular component or subsystem. And finally, we can test filters, cables, amplifiers, antennas, crystal oscillators, and more because, again, we can visually see the frequency ranges and the actual frequency footprint and amplitude directly on the spectrum analyzer display. I'd like to demonstrate a VSWR test for this components section of this particular video. And a VSWR test, for those of you that are not familiar, stands for voltage standing wave ratio measurement. And that is typically done on an antenna or an antenna network. And the VSWR is a measurement of the quality of the impedance match between the antenna network and a 50 ohm network in this particular case. So to perform that particular test, we're going to need a spectrum analyzer with a tracking generator option. Again, the tracking generator is a swept RF source. That sweep, the frequency sweep, matches the detector. You can see this instrument sweeping across. That tracking generator, when it's active, is sourcing a frequency that's changing at the same rate as the detector in the same steps. You're also going to need a reflection or return loss bridge. In this case, we're going to use the Siglent RB3X20. That's a 2 gigahertz reflection bridge. And what's going to happen, the RF energy is going to come out of the tracking generator, go into this reflection bridge, out to this device under test port. If we have a high impedance here or a big difference in impedances, the energy is going to reflect back into the instrument. That is going to then measure as a high value in amplitude as we sweep across the frequency range. As long as that impedance stays very mismatched, it's going to show a straight line. When that impedance is matching, so there are frequencies, we hope, there are frequencies where this particular antenna is going to resonate. It's going to actually pull energy out and radiate. When that happens, we're actually going to get a dip, and that dip is going to show us that at minimum point of that dip is going to be the maximum point of, or the maximum point at which this, or efficiency of this particular antenna, so the frequency at which this antenna radiates most effectively. So I'm just going to pause for a second and attach this to the instrument. I'll be right back. Okay, so you can see now that I have the reflection bridge attached to the front panel of that spectrum analyzer. I'm just going to set the camera down there, and I'm going to attach our antenna that we had previously. Actually, I'm not going to do that yet. I forgot one important step. So the tracking generator now is not configured currently to be on. We're going to press mode. We're going to go to reflection measurement. This is part of the option for the reflection measurement kit on this particular instrument. We're going to press reflection measurement, and you'll see that it says cal open. What we'll do is we want to open, so I have an adapter here, but I want to subtract the impedance of this particular adapter from the measurement of the device under test, which again is just this antenna. I'm going to hit cal open, and you'll see that it'll flatline. Now what we've done is zeroed out the reflection from this particular adapter. Now we have a flat blue line up at the top. I'm going to change the reference level just a bit so you can see the line move down. So now we're measuring 0 dBm here, and now I'm going to then attach the device under test, which is this particular antenna, and now you'll see the reflection. So areas or frequencies that we're getting direct reflection are going to be shown as dips, and you can see that there's a very nice dip here. I'm going to turn the marker state on, and I'm going to rotate it to that lowest point that is going to measure the VSWR at that particular point. And you'll see as I get closer it changes the impedance, so it is a little bit difficult when it's mounted directly up there, but that's a pretty good reading right there. And we've got a VSWR of around 1.1. And this gives our return loss value at that particular point and our reflection coefficient. So this particular antenna in this configuration resonates most effectively at 170.8 megahertz. And you'll see that if we change the height of that, you'll see that that peak is going to change. So I'm just going to rotate back through there, and you'll see that that frequency has changed to 200. So by changing the length of that antenna, we're actually changing the resonant frequency of the antenna network, which makes sense physically, and should be all set. So there are some very nice automated features with many spectrum analyzers that can allow you to characterize many RF components in a simple way. Now I'd like to take a closer look at EMI pre-compliance applications. With the EMI pre-compliance, what we want to do is design to pass compliance the first time. We want you to go to the lab once, and we want you to have your certificate of compliance afterwards and get right to selling product. No use going back in and redesigning and trying to pass compliance over and over again. As for those of you that do know, compliance testing is expensive, and having to go back repeatedly can definitely hit you in the wallet, so we want to minimize that. We want you to find and fix problems before you even get to the lab. With a spectrum analyzer like the Siglent SSA3000X, you can do a lot of work and troubleshooting ahead of time, solve a lot of those easy to find problems, even some of the more difficult ones, before you ever even get to the lab. Have that all squared away and a very good understanding of where your EMI or your EMC output or footprint happens to be. And then finally, we want to minimize test time and decrease time to market, and a spectrum analyzer is definitely going to help you do that. And now let's take a closer look at an EMI application. In this case I have the SSA3000 or 3021X, and I'm going to be using a near field probe. This is a magnetic near field probe, the Siglent SRF 5030. And what you can do with a near field probe is as you get closer to a source of radiation, you'll see the display. We start to get quite a bit of RF going on as we get closer to the DSP in this particular design. And in this case, if we had the cover over this, we would be able to sniff around the cover to see if there were any leaks for EMI, and we'd be able to say make suggestions on whether we needed to gasket a particular output or perform some kind of shielding in order to minimize that RFI. And basically you're just going to go across your design and take a look at the areas that are going to be the most likely to cause any issues. This isn't a direct indication of a failure from an electromagnetic compliance test standpoint. Again, the near field probes are typically used for troubleshooting, so you may already know where your issue lies, and now you can sniff out, they do also call them sniffer probes, you can sniff out the areas that may be most problematic on your design, and in that way the spectrum analyzer can help you with the use of these probes to find those particular problem areas and make corrections accordingly. Here's a quick checklist of spectrum analyzer features that may be helpful as you do a search for your instrument. You're going to want to look for a low noise, or DANL, that's displayed average noise level. If you're in the minus 150 dBm range, that's going to be helpful for finding very small spurs and harmonics. We also want you to look for a minimum resolution bandwidth of around 100 Hertz or less. The smaller the minimum resolution bandwidth, the better resolution you can see between two particular signals. Let's say we had signals that were 200 Hertz apart and we had a resolution bandwidth of 100 Hertz. You would see two distinct signals. 200 Hertz. If our resolution bandwidth was bigger than the separation between those two frequencies, we would actually see just one signal on the spectrum analyzer. So we wouldn't be able to even tell that there were two signals underneath that umbrella or envelope of that measurement. So smaller resolution bandwidths are going to give you lower noise. They're also going to provide you more resolution or smaller resolution between frequencies. We're also going to want to have a faster sweep speed. The faster sweep speed we have, the faster we can collect data, the faster we can get done with our job. You're also going to want to look for low phase noise. We want our phase noise of the measurement instrument to be considerably less than the phase noise of our device under test. This is especially important if we're measuring transmitters and oscillators. I also want a tracking generator. If you're going to be measuring passives like filters, cables, adapters, also doing reflection measurements or VSWR measurements, a tracking generator is going to be essential. It is an RF source that follows the sweep of the spectrum analyzer. So it's actually going to source a RF signal that could have a changing frequency, and that's going to then go through your passive and into the RF input, and you'll be able to actually trace out the actual frequency footprint for that particular device. On-screen measurement options are also helpful. This includes VSWR, third-order intermodulation, adjacent channel power, many on-screen measurement options, again, depending on the personality type of the instrument that you purchase or that you're looking for. And we've got EMI specific test options as well. That's going to be special resolution bandwidth or RBW values, quasi-peak detector, and an EMI filter that are going to help provide data that is going to more closely represent that you would receive from a full EMI receiver or EMI test setup. So we hope that you have found this presentation to be helpful. Again, if you have any questions, please contact your local Siglent office. Thank you and have a great day.